Good morning. We're going to do some problems with Gauss's law and get into the discussion on potential. So as we have seen in the last lecture, for Gauss's law, we looked at the surface integral of E dot dA, where dA is the area element. So we're looking at the surface integral over a surface, and we saw that this was Q enclosed by epsilon naught. And by using the fundamental theorem on divergence, we were able to see that this could also be expressed as divergence of E is equal to rho of R by epsilon naught. Now let's use this Gauss's law to solve a problem. We're going to pick an infinite plane of charge. So here we have an infinite plane, and this has a uniform charge density. So this is uniform charge density of sigma. So now, if you just look at the symmetry of the infinite plane, for example, let's go to a distance, x above the plane, the infinite plane charge, and say we stand here at point A, right? So from point A, it appears that you have, you have this much view of charge, let's say, of the infinite plane. So you are able to view whatever is within this cone. And if you go to, say, point B somewhere else, which is also a distance x above the plane, right, you will still see the same amount of charge. You will still see the same amount of charge, right? So at point A and at point B, which are both at a distance x above the surface, you would expect the electric field to be the same. Now, what about going higher? For example, instead of x, if I have gone to 2x, right? Then I'm essentially going to see, more charge because I'm farther away. So let me do that with green color. So I'm able to see, more charge. When I was at A or B, I'm able to see, this much charge. So when I'm at C, I'm able to see more charge, but C is farther away, right? So the electric field should be weaker as you're going farther for a point charge. But here, as I'm going farther, I'm able to see a larger intersection of the charge. So there is more charge. So whether you go at the same distance or away from the plate, the electric field for an infinite plate would be constant. Because as you're going farther away, you would see that there is more and more charge in your view. And so that extra charge that you're seeing is compensating for that 1 over r square effect of a point charge. So the electric field from infinite plane would be constant. So with this simple argument, now you can see that the electric field of the infinite charge sheet should be pointing up when you're on the top, and when you're at the bottom, it should be pointing down. And it is constant throughout. So now we can choose what we call as a pillbox. So this pillbox is essentially a box, an imaginary Gaussian box around which we are going to perform our surface integral, right? So this is extending below the surface as well, right? And let's consider that this Gaussian pillbox, which is a cube, each face has an area of A, let's say. Right, now we know that the E field when you're on the top is pointing up, and E field when you're at the bottom is pointing down, and this is constant throughout. Now if we were to go around the surface of this Gaussian pillbox, right, we're going to go around the surface of each face and integrate to get the total surface integral of E dot dA. Then you see that when I take these faces that are here, the side faces, the area vector for the side face, for this side, it's pointing this way, the area vector. And for this, the the area vector dA is pointing this way. So both these faces, the side faces, they have area vector pointing perpendicular to the direction of the electric field, so they don't contribute to the integral. Same thing with the front and back faces, right? So front and back faces also have E is perpendicular to the area vector. So sides and front and back don't contribute anything. Only the top face and the bottom face contribute to the surface integral. So now if I were to do this, then that should be simply twice of either the top surface, the integral over either the top surface or the bottom surface, because they both of them are equal. The electric field is constant, and on the other side of the plane, down is the direction for electric field, and the area vector is also pointing down. So this is negative direction, this is negative, and both of them give positive, just like the case of top, where dA and E both are pointing upwards. So that's why we have a summation 2 here. So because electric field is constant everywhere by the symmetry arguments we just made, we can pull it out to E, and essentially I only have integral over dA, so that is 2EA. But from Gauss's law, we know that this should be equal to the charge enclosed by 2 epsilon naught. Sorry, charge enclosed by epsilon naught. So we can equate this to charge enclosed by epsilon naught. So if I just want to figure out E, then E is equal to charge enclosed by 2A epsilon naught. But charge enclosed by area essentially gives you the charge density, and here we have the charge density to be sigma, so then the electric field is sigma by 2 epsilon naught. And then we can give it a direction, because we know that it's pointing upwards when you're on the top and downwards when you're on the bottom side. So we can give it a direction with the vector n, which points up when you're on the top side, and down when you're on the bottom side of the plane. So that's the electric field, and you see that indeed, it is constant. Of course, we made that argument to do the integral, but as you can see from common sense argument that as you're going farther away from the infinite plane, your view, the extent of the plate that is in your view is increasing, so you're intercepting more charge, and this more charge as you're going far away is somehow compensating for the 1 over r square effect that would otherwise come from the point charge. So that's why you see that electric field of an infinite plane is constant. So now let's take this example to understand potential in greater detail. So now imagine I have a slab of charge here that's placed this way. We're extending this way. I'm just showing you a cross section here, where I'm just cutting it off in middle here, right here, to show you a cross section. So this, we know that the electric field should be sigma by 2 epsilon naught everywhere, pointing this way to the right, or now I just tilted the infinite plane, so on the other side it will be pointing that way. So now if I look at the planar around this plate, we know that there is this charged plate that is causing electric field in planar surrounding it. So if I look at some planar, right, and divide this into several cells here, the planar that's right next to it, and here the electric field in all these things is the same, because electric field is constant, right? So all these, if you go anywhere in these boxes, whether you are here or here or here, you're seeing the same electric field, because electric field is constant. So this electric field itself is not really giving you any idea directly. So if I take electric field at this particular point in this particular planar cell, this electric field itself is not giving us, at this particular point itself is not giving us any information about the energy. So we can think about this in another way, that is using the potential. So we have seen in the last lecture that E can be expressed as grad phi. So I can rather view this planar in terms of this phi, a scalar potential function, and assign to each cell in the planar a scalar value for phi. So phi would have one value for each box, just like how electric field had one value. And the use of that is it sort of tells us about the work done. So for example, imagine you bring a test charge. So we're bringing in a test charge, Q. Let's say we are going from a cell A to cell B here. So we're taking this test charge Q from cell A to cell B in the planar under the influence of electric field generated by the slab, which is given by this. So we can write then the work done by the electric field itself. That is, there is an electric field and you're moving the charge in it. So there's work done by the electric field, which is going from A to B, Q times E dot dx. Here we have QE because work in general is F dot dx. That's the work done. But the force on the Q, the electric field itself has the ability to give impetus to the field to the charge. So that's why the force on it is QE. So we simply plugged in QE here, and that's how we got this. So then I have this as I can pull out Q. I can go from E to B, this E dot dx, right? So now if I look at this integral itself, this E dot dx in general, this E dot dx, if I give it some, this is essentially a dot product here, E dot dx, so I'm integrating it. So I should get a scalar quantity when I perform this integral. So I'm just going to get a number. So if I give here some function phi or minus phi, we'll see why we want the minus sign here a little later. Then I can write this as Q times this integral itself is minus phi, right? So I would have minus phi at B minus phi at A. So then that means this would be Q times this gives you positive phi A minus phi B. So now, like I said, from if I assign a scalar potential to each box, so if I assign, this is phi A, this is phi B, and this is phi C, then if I am going from A to B, and if I look at the difference between these two potentials, phi A and phi B, that sort of tells me how much work is done by the electric field, right? And because this is directly related to the internal energy, the change in energy delta U, right? Because there is force that is changing the impetus, so you're changing energy. So this is related to that. So this function, the scalar potential function, is somehow telling us what is the difference between each cells in terms of how much work would be done if I were to go from point cell A to cell B. It is directly telling us through this the difference. So it is giving us a further specification of the electric field. In case of the slab here, the electric field was same all throughout, but the potential is not same. So because the potential is not same, it is telling us a little more information that if you move from point A to point B, right, there is going to be a force, and that force is going to do some work, and that's going to be this much. So although we have not discussed in greater detail why potential should be a quality of the planar, later you will see that whether in quantum mechanics or electrodynamics, we will see that potential is indeed a power or quality of the planar. So then that is the use of our potential, that it is giving us. So in case of the infinite charge sheet, in fact, I can then write for each cell a certain potential, and that's very easy to write because we know E is equal to sigma by 2 epsilon naught. So all I need to do is get E dot dx, right, which is sigma by or minus of it to get phi, sigma by 2 epsilon naught dx, or that is equal to minus sigma by 2 epsilon naught x, right? So let's say this is x is equal to 1, x is equal to 2, x is equal to 3, x is equal to 4, so on and so forth, right? Then I can simply give a value of minus sigma by 2 epsilon naught um, for all these cells, and this would be minus sigma by epsilon naught for all these cells, and this would be minus 3 sigma by 2 epsilon naught, right? So I can provide these potentials as I am going farther from the plate. As you can see, these are not the same. And electric field being a vector, you need at least two cells to define a direction. If I want to define a direction in this planar chart, then I need to compare the cell I am in with some other cell. So if I compare it with this, I can define this direction. If I compare it with that, I can define that direction. So you need at least another cell. And so this potential, which is different at different cells, which is a further specification of the electric field, is actually also telling you about the direction of the electric field itself. So the gradient, the potential is built in such a way that the gradient is giving you the electric field, whereas the potential itself, the value at A and B, the difference itself is giving you work done per unit charge. So now let's see what should be the potential for a point charge. So for a point charge, we know that E is equal to kq by r square r. So we want the potential to be such that negative of grad phi gives us E. So we could do the integration with E dot dr, right? So if we do that, we can see that very simply phi comes out to be kq by r, right? And this is very easy to verify. So if I do negative grad phi, then that would be negative gradient of kq by r. So and that would give me negative of negative kq by r squared times r. So sorry, this should be a vector. This is a unit vector, not the r itself. So that would be kq by r squared along r. So this is a potential for a point charge. So here, as you can see, when we say coming from infinity, the potential is zero. What we mean by that is that we're bringing the charge from very far away, where the interaction with other charges is there is no interaction with other charges. We're bringing it from such a place, not really from infinity. So now, if I have any randomly charged shaped charge distribution, something like that, then I can measure the potential at a point P due to this charge distribution. So I can say that this point P is at a distance r from the origin. And then what I'm going to do is I'm going to divide this charged body, like we had done with Coulomb's law. I'm going to divide this charged body into tiny cells, right? I'm going to divide this into tiny cells, and then I'm going to label each cell. I'm going to label each cell with r prime. So r is the vector connecting the origin to our point of interest P, and r prime is the vector pointing to each cell, right? So and then I'm going to go over each cell and some of their contributions. So first I'm going to look at the contribution of one cell, right? To do that, let's say this entire charge body has the total charge of Q, and a volume of V, right? So we're going to take a rho, right? Or in general, we can just take rho as a function of r prime itself, right? And so then if the rho here at r prime is rho of r prime, that is the charge density, then to get the total charge, we multiply the charge density at r prime with the total volume. So the total volume, I'm writing it as d cube r prime, to indicate that it is length, width, and height. But in r prime, because r prime is the coordinate we're using to measure the distance from origin to each cell. So then the potential due to this one tiny cell at point P would be K times the charge is this rho of r prime and the tiny volume element d cube r prime divided by the distance between the cell and point P. And from simple vectors, you can see that that distance would be r minus r prime. So then this would be r minus r prime. So this is the potential from one cell. So if we want the potential in general for the entire body, we move this vector r prime over each cell. So we go to each cell across the body, and then so essentially we're doing an integral. Right. So if I do an integral, I'm summing up over all the cells. So then this gives us the potential at point P. Right. So this is the potential at point P is given by that. So now let's look at another thing with the with potential. We define E is equal to negative grad phi, but from Gauss's law we know that the divergence of E is rho by epsilon naught. So then I can plug in this here. So I'm taking divergence over gradient of phi, which gives me negative divergence of gradient. Recall that we call this as the Laplacian. So here we have a Laplacian phi, and this is a scalar function, not a vector function. So you have to do the Laplacian like how you did in homework 2. So this should be equal to rho by epsilon naught, or del square phi is equal to minus rho by epsilon naught. Right. This sometimes is written as negative 4 pi k rho. So k is essentially there 1 by 4 pi epsilon naught. So sometimes it's also written like this. So now this is called the Poisson's equation. So this is Poisson's equation. Now, if we look at the special case of this equation where the Laplacian del square phi is 0. That is, for example, where there is no charge, right? So this del square phi is equal to 0 is the Laplace equation. And the solutions to this Laplace equation are called harmonics. We will look at this in more detail as we go into chapter 3. And we can use the solutions to these equations to, in general, approach how to solve the Poisson's equation depending upon what the charge is. So here, this is no source. There is no source. There is no charge pumping out electric field into the planar around it. But here, there is a source, right? So this is without the source, and this is with source. So we can use the equation, Laplace's equation solutions in general to see how a lot of times the solutions to Poisson's equation look like. But let's go back to what we wrote, how we described phi for any charged body. We saw that phi was a function of r. So the phi at any given place r, we wrote it as k times rho of r prime d cube r prime divided by r minus r prime. These are vectors, right? So then I can treat this denominator, which is a function of r minus r prime. So I can treat this as a function of r prime. And what we would like to do is Taylor expand this function around the origin. That is r prime. We'll set r prime is equal to 0. Right, so we're going to Taylor expand this potential around r prime is equal to 0. So for that, what we need to do is I have f of r prime, but this r prime is a vector. That means I can write this r prime as some ri. So this I is repeated, so it is summed over. So it has three components, x, y, z, for example, or r, theta, phi, whichever coordinates you choose. But there are components along each coordinate because it is a vector, right? So then, if I Taylor expand that, the first term would be simply f at r prime is equal to 0. Then the second term is you have three coordinates, right? I goes from, this is sigma I going from 1 to 3. So you have a sigma I going from 1 to 3, right? You have ri prime. We are expanding around r prime. So for each component, you have ri prime, dou f by dou ri prime. And then for the next one, we have again three these things and half. But now you have a second derivative, so you have ri prime, rj prime, dou square f, dou ri prime, dou rj prime. So we can expand it that way. And we are doing this expansion to come up with something called the multipole moments, which will be very useful for solving a lot of problems very easily. So that's the idea of Taylor expanding this function, the denominator here in the potential, using Taylor expansion. So now we know our function, so we can do the derivatives, dou f by dou ri prime and dou square f by dou ri prime, dou rj prime. So let's get to that. So first we will do dou f by dou ri prime. So we are doing dou by dou ri prime of 1 over r minus r prime. So if you look at this r minus r prime, right, this r minus r prime is essentially something like, square root of x minus x prime square plus y minus y prime square plus z minus z prime square, right? Or I can in general write it as some component k minus component k prime, the corresponding component, squared, and that's summed over k, right, and then to the power half. We have to write the components explicitly because the derivative is with respect to the components here. And notice that the square doesn't cancel with this half because we have a sum. So the square root is a sum of squares. So we cannot just cancel out these two. So you ought to pay careful attention there throughout electricity and magnetism to not do those errors. So then I can write this as dou by dou ri prime 1 by, I'm not going to write sigma k because it's repeated, so it's summed over. So r prime square whole to the power half, right? So that would give me minus half, right? 1 over rk minus rk prime square to the power 3 by 2 because I differentiated. But then I have to do the dou ri prime of rk minus rk prime square. So that would give me minus 1 over 2, 1 over rk minus rk prime square whole to the power 3 by 2. Here I have ri prime, that's what the derivative, my derivative is with respect to, right? So I'm only bothered about those terms where I and k are the same thing, because if I have dou y by dou x or dou z by dou x, those are essentially 0, right? I'm only worried about dou x by dou x. So only when this I prime and k prime are equal do I have a non-zero term. So I'm essentially going to get a 2 here, and then ri minus Ri prime. I change the index here from k to I because that's the only term, because we're doing the differentiation with respect to the ith term that survives. And then the differentiation of R prime itself gives you a -1, right? So then you have this -1, 2, and these canceling out. So then I can write this as Ri, excuse me for that, Ri minus Ri prime divided by, Rk minus Rk prime squared to the power 3 by 2. So this is simply writing it as Ri minus Ri prime by R minus R prime whole cube, right? Because this 2 and 1 by 2, they give you R minus R prime, right? So that's the result for dou f by dou Ri prime. Now let's do the second derivative. So the second derivative is dou squared f by dou Ri prime dou Rj prime. So this would be dou by dou Ri prime of dou f by dou Rj prime. But we already did this. We know how this should look like. So we know that we're going to do dou by dou Ri prime. From the last slide, the result of this is Rj prime by R minus R prime cubed, right? So then I would have two terms here by chain rule. One is dou by dou Ri prime of Rj minus Rj prime times 1 over R minus R prime cubed plus Rj minus Rj prime dou by dou Ri prime of 1 by R minus R prime cubed. So if I do this, right, the first term is 0 because I'm differentiating with respect to Ri prime. So I have 0 minus, I have I here and j here, so this will be 1 only if I and j are equal. So I'm going to use a Kronecker delta and indicate that as delta ij, and here I have R minus R prime and to the cube, plus here I have Rj minus Rj prime, and I'm doing dou by dou Ri prime of cube. So I would get, essentially, if I rewrite this as Rk minus Rk prime squared to the power 3 by 2, then I'm going to get minus 3 by 2, 1 by Rk minus Rk prime squared whole to the power 5 by 2, and then I have to do a derivative of Rk minus Rk prime squared, right? So that's going to give me here, the first term is negative delta ij divided by R minus R prime cubed, and the second term is the Rj minus Rj prime multiplied by minus 3 by 2. Here in the denominator I have R minus R prime to the power 5, and here I would get 2 and Ri minus Ri minus Ri prime times -1, right? So then this 2 cancels out, this negative sign cancels out, right? Then I would have essentially minus delta ij by R minus R prime cube plus Rj minus Rj prime times Ri minus Ri prime divided by 3 times that, divided by R minus R prime whole to the power 5. So now I can take this as a common factor then, and if I do the common factor, then I can see that dou square f by dou Ri prime dou Rj prime would be equal to a common factor of R minus R prime to the power 5, and here I would have with delta ij R minus R prime squared, because as you see in the previous here, this is a cube root, so I have to multiply the numerator with a square so that I get a cube here. I get to the power 5 there, so that's why I have that, plus Rj minus Rj prime, Ri minus Ri prime, there is a 3 here, I think that's it, right? So that's dou square f by dou ri prime dou rj prime, and simply dou f by dou ri prime we saw was ri minus ri prime by r minus r prime whole to the power 5. These are vectors. So if we go back to the scalar, the Taylor expansion of the scalar potential, we wrote that function at r prime, at r prime is equal to 0 plus we had ri prime dou f by dou ri prime. The summation is implied. Similarly here the summation is implied too. Dou square f dou ri prime dou rj prime. So then function at r prime is equal to 0, right? Our function is 1 by r minus r prime is our function of r prime. So if r prime is equal to 0, then this function is simply 1 over r, right? And plus this is also at r prime is equal to 0. This is also at r prime is equal to 0, and so on. So here I have ri prime, dou f by dou ri prime is this. So I have ri minus ri prime, r minus r prime to the power 5. I take r to be 0 only in this factor. I'm setting r prime to be 0 only in this factor. So if I do that, each component itself is 0. So this is 0, right? There should be a cube. Sorry, that should have been a cube. So this would be 0 too because I'm setting it at the origin. So then I would have here there is another half factor plus half ri prime rj prime this here. So ri prime and rj prime would be 0. So I would have 3 times ri rj minus delta ij r square, right, divided by r to the power 5, because I'm setting r prime is equal to 0 here. So all the r primes I'm setting 0. So then this function of r, when Taylor expanded, would look like 1 over r plus ri prime times ri by r cube plus half ri prime rj prime 3 ri rj minus delta ij r square r square divided by r to the power 5. So then we can plug this back into our potential, right? That was our main goal, to Taylor expand the potential. That's why we chose this function and Taylor expanded it. So we can place this Taylor expansion back into the potential. So the potential itself at phi at r was written as k times rho cube of r prime d cube r prime divided by, these are vectors, divided by r minus r prime. So we Taylor expanded this, so we can plug in the Taylor expansion there. So we would get for the first term, we would have rho at r prime d cubed by r prime. The first term itself was simply r. So the Taylor expansion of f of r prime was 1 over r plus ri prime by r cube plus half ri prime rj prime 3 ri rj minus delta ij r square divided by r5. This was what we got on the last slide, and I'm simply substituting these factors. Then I have the second term to be k times rho of r prime d cube r prime, this ri prime divided by r cube. Similarly, the third term would be rho of r prime into this term, which goes as r to the power 5, right? So we call this looks like kq by r, like a point charge kq by r, right? So we call this as the monopole. And here you have two, ri prime. So this we call it as dipole. And here you would have four, ri prime, rj prime, and ri rj. So this would be a quadrupole. So these are different multipole moments. Or we can think of this as a total charge, right? If you look at this integral, we can think of this q of rho of r prime, d cube r prime, as the total charge enclosed, right? So we call this as a monopole. Similarly, we can define a dipole moment. A dipole moment we can define from here by combining all the r prime terms. So I'm combining all the r prime terms. So then I would have the dipole, this is monopole, as ri prime, rho of r prime, d cube r prime. Similarly, I can define